Welcome back. In this video, I'm going to walk you through one more example of the z-test. Now, if you look at the material for these that correspond to these videos, you'll find that there is another null hypothesis significance testing in class example z-test. There's a 1, so this is the second example. So I encourage you to walk through it as well. It's set up the same way. But in this scenario, and I apologize, I'm just going to end up reading a bunch of this to you, but it's one more example on top of Dr. Meyer. All right, so in this example, Dr. Lawrence is interested in the effectiveness of occupational therapy on the performance outcomes of first grade students. Dr. Lawrence knows that the population mean for first grade students on a measure of performance called the Bren test is 110, standard deviation of 12. Dr. Lawrence is interested in whether students who have previously been enrolled in occupational therapy for a period of 3 years scored differently on the Bren test than those not previously enrolled in occupational therapy or the general population. So again, if we think about our chart, this is a z-test. A z-test is appropriate here because we have one sample and we want to compare it to, and we want to compare our sample to the population, and the population mean and standard deviation are known. So if I look back here, this qualifies. I know the population score on this measure is 110 and the population standard deviation is 12. Well, Dr. Lawrence wants to know kids who have been enrolled in occupational therapy, are they scoring the same as just kind of the population mean? All right, so first we're going to state the hypothesis. Well, the null, remember the null always says there are no differences. So Dr. Lawrence's null says the occupational therapy kids mean is the same as just the general population mean of first grade students, okay? Now, her alternative, she is specifying is non-directional. So she's just saying, you know what, I don't think they're going to score the same, but I'm not sure if they're going to be higher or lower. So I'm just going to say no difference. And honestly, if you, in your own research, you can certainly state a directional hypothesis and still use the non-directional test. And I'll tell you why. The non-directional test it's harder to find significance. And you might have to think about that for a minute and go back and revisit the part 2 of the hypothesis testing. But if you remember how that probability was split in a non-directional test, so for us to find significance, our probability, our obtained probability, has to be even smaller than a one-tailed test or a directional alternative. So even if Dr. Lawrence really feels like occupational therapy kids are going to score better, it's perfectly fine for her to write that and then run a non-directional test, just because this is harder to find statistical significance. Okay, I hope that makes sense, but here we go. Okay, step 2, draw the sample and calculate the mean. So Dr. Lawrence draws a sample of 36 first grade students who have been enrolled in occupational therapy for the previous 3 years. She gives them the Bren test and then calculates a mean for her sample. Her sample mean is 114. So now, using the z-test, she can determine the probability of her having obtained the sample mean of 114 if the null is true. Remember, the null says there are no differences. So the null says that occupational therapy group is also 110. All right, so convert the sample mean of 114 to a z-score, or do the z-test. So we're going to take our sample mean, subtract the hypothesized population mean, and divide by the standard error. All right, So, and remember, the standard error is the standard deviation of that sampling distribution. All right, so but I remind you here, what's the standard error again? The standard error is the population standard deviation, which is 12, divided by the square root of 36. So 12 divided by 6, that's 2. So the standard deviation, or the standard error is 2, or the standard deviation of the sampling distribution is 2. Now I can divide. So I go back to my formula. 114 minus 110 divided by 2 gives me 4 divided by 2 and a z-score of 2, right? So if I am thinking about that curve, sometimes it helps me to picture it. Actually, a lot of times it helps me to picture it. So if I have my line and I'm imagining that curve, oh, that's terrible, and I have a z-score of 0, because these are z-scores down here. I know they have a standard deviation of 1, so my z-score of 2 is going to be right here. So I'm going to look for this probability. What is this? So I can go to the back of the book. So using the table in our book, the area beyond the z is 0.0228. So the probability of Dr. Lawrence obtaining the sample mean of 114, if the null is true, is what? If we round it, it's 2.3, we could say 2.3%. So the probability of her having obtained the sample mean she got, if the null is true, is 2.3%, which is pretty tiny. So here's where we start thinking about that indirect logic, right? So if that probability is really tiny, if the null is true, maybe the null is not true. All right, so now we're going to say, is this probability tiny enough? So we're going to compare the obtained probability to the critical value we've chosen. For this study, we chose an alpha value of 0.05, which we will do most of the time, right? Because that is our standard that we know from social science research. That's just the critical value that 99% of people use. But we have to remember, we did a non-directional test. Okay? So we have to double our obtained probability value. And remember, this is what I told you SPSS is going to do for us. Now, we have to do it ourselves here, but from now on, when we use a computer, we're going to be given this. It's going to be called our SIG value. So we're going to take our obtained probability of 0.0456, compare it to 0.05. It's still less than. So for us, well, I was going to put a smiley face, but really, let me think about this. This result is statistically significant. If we find statistical significance, we reject the null hypothesis. Remember, that says OT students also have a mean of 110. All right, so let me just kind of say it one more time, because I know it can be a little confusing with this indirect logic. So the probability of Dr. Lawrence obtaining the sample mean she obtained, which was, remember, 114. So the probability of Dr. Lawrence obtaining a mean of 114 is, well, it is this, but we know a two-tailed test, we've got to double it, is this. So the probability of Dr. Lawrence obtaining a mean of 114 is 0.0456, which is really tiny. In fact, it's even less than our alpha level, or our critical value. Therefore, we're going to conclude that the null is probably not true. And remember, the null says this. So we don't ever have proof. You know, if you have a true experimental design, you could come the closest to talking about cause and effect. But what we have here is the probability of obtaining the sample mean we have, if the null is true, is really tiny. It's smaller than our critical value. Therefore, we're going to conclude that the null is probably not true, and we're going to reject that null and say that occupational therapy students don't have a mean of 110, or they don't score the same as just your general population of first grade students. All right, let me scroll down for a second. So, and I wrote some conclusions there, and what I want you to note here is that, very confusingly, I'm sorry, but that 0.05, that critical value or that comparison value we're using, has a bunch of names. I don't know why they couldn't just all be consistent, but it's going to disappear again. Poof, it's gone. Okay, anyway, that 0.05, it's also called alpha level, critical value, probability of type 1 error, p critical, and there may even be some more. But all of this, if you see it written or talked about, it all means the same thing. It all means it's that 0.05 for educational research and actually social science research. I'm going to wait on this. I'm not going to talk about this. We're going to talk about something called confidence intervals in a few lessons. And so I'm going to save this discussion until that point. So again, I would encourage you to go back to Blackboard, pull the other example, and kind of walk yourself through it, because what's important here is that you understand why we're rejecting the null, at what point we decide to reject the null, and kind of how that works, because now we're going to move what we're doing onto the computer, onto SPSS, as we continue and look at the next test of significance. And it's going to be important that you have this underlying understanding, because even though we're not going to be up here calculating our test statistic, which in this case was a Z, we're not going to calculate our test statistic anymore by hand. SPSS will do it for us. We're not going to look in the back of the book for our probability. SPSS will do it. But you need to have an idea of where this information comes from and what it is telling us and what it's not telling us. So I would encourage you to revisit this video and then look at the other example before you continue to the next test.